Harshit Dagli, and I'm a TEDx and TED speaker. I'm also a Google certified mobile site developer, and you can find me giving sessions on AI at different events. And I also lead a Mozilla Campus Club, and I'm a GitHub campus leader too. You can find me on any of these links and ping me if you require any kind of help. So yeah, so a bit refresher in AI point of view. So these are some of the milestones in AI. So I think all of you know about this, how AI started with the Turing test. So Turing test, I don't have to explain it. Then another milestone in AI was in 2014, GANs or Generative Adversarial Networks. That was another milestone for us. And if you know about Microsoft Project Brainwave, it Project Brainwave is like a deep learning platform for real-time AI and inference in the cloud and on the edge. So you can use Microsoft's Project Brainwave to for using deep learning techniques on FPGAs, programmable arrays, and also use RNNs with Bing with no batching required. So if you haven't tried that, I would recommend you all to try the Project Brainwave and see what all it has. So yeah, we'll come to the part why bother at all about what's happening inside an AI algorithm. So the first thing, it's not easy at all. There are so many variants of this. So you must have seen linear regression. We have gradient descent to solve a linear regression problem. In gradient descent, we have so many variants like jackknife or batch size and things like that. So there are so many variants, and it's of course tempting to directly use libraries when you can get them in 5 lines of code or so. So you can easily get done in 5 lines of code with scikit-learn with a logistic regression algorithm on iris dataset with a pretty good accuracy. So, or you could also use TensorFlow to get done in few lines of code. So again, why do we need to bother at all about what's happening inside an AI algorithm? So I feel that pre-made models are good for learning and not for industry. This might be an arguable topic, but I'll tell you what I have in mind. So you would ask me why Azure or GCP or scikit-learn models are made. So now, according to me, I think you could use these models, make some modifications, but you need to know what's happening inside, because it's pretty much possible that you get an industry problem where if let's say your feature x1 is below some value 0.5, it seems to be a linear regression algorithm, linear regression fit, and if it's above 0.5, it seems to be a polynomial regression curve. So which algorithm do you use? There's actually no specific answer to this. You might say if x1 is below 0.5, I'll use linear regression. If x1 is greater than 0.5, I'll use polynomial regression, and I'm done with the libraries too. But notice one part, that AI is not about feeding data and making predictions on the data which we already have. It's like taking a trend out of the data. So in this case, what would happen is you'd pretty much face a smoothing problem. So the convergence of both these, if you plot them on graphs, you will need to smooth that. And for that, you need to know what's actually happening behind the algorithm. Because currently there exists no such algorithm in the market which can smooth the linear plus polynomial regression curve. Yeah, and libraries are easier, but as I told, so I think we are all familiar with linear regression and gradient descent and what actually happens in the math behind it. So there's no need to explain it, but we'll take a quick refresher in few moments. So what we'll do is we'll explore logistic regression algorithm and make the logistic regression algorithm from scratch. So logistic regression, as the name suggests, but it is not a regression algorithm. Yeah, I'm sure. So why logistic regression at all? So in most cases, logistic regression is just enough. Like we'll see the examples of MNIST and Visconen too. These are names of the data set. Logistic regression algorithm works very well with powers, and in industry problems, things can't be as simple as a linear regression with x's. It can be a regression with x1 into x2 or x2 squared x3 cubed and things like that. So logistic regression comes to our aid in that, and it works very well with powers. We'll actually explore this point in a few moments. A logistic regression algorithm always tends to zero but is not equal to zero. So what that means and how is it even useful to us, we'll see that. Another thing is that logistic regression is important and like a base for understanding the most common NNs. NNs are neural networks, if you didn't understand the analogy. So now we come to the part why the thing that it tends to zero and is not equal to zero is helpful to us at all. So let's take the step function for example. So step and ReLu are activation functions in neural networks. So why we would want to use the sigmoid function or the logistic regression in a neural network? We'll see that. So step function is a graph like this, and the problem in this is that it gives us a zero value over here. So let's say um, if at some point in your neural network, if you get a zero from the activation function, your gradients will stop optimizing. It will say that I'm fully optimized. I can't optimize my gradients anymore, and we don't want that. So for that, a ReLu function was built, which was a better fit than the step function itself. But in few of the demos we'll see later and live coding sessions, we'll see that ReLu 2 gives us some problems, like the dying ReLu problem, where the gradients don't update themselves. Cause ReLu 2 tends to zero over here. So how so let's see sigmoid function and how it helps. So this is a logit function, or you might also call it sigmoid function, and this is a simple example of it being applied on probability of passing the exam versus hours of studying. So the logit function is something like this, and we want to replicate this. So we like want to build a AI model for it. So you might find logistic regression as finding the best beta parameters that fit beta 0 plus beta 1 plus e greater than 0 if y is 1, or else or else if y is 0. But don't worry, I'll simplify this a bit for you so we can understand it and make an algorithm for it. So first we need to find out the equation of the function of the graph which I showed you. So let's actually see how I would like find out the equation for it. Okay. Okay. So we see that a function e raised to x, we want e raised to x because we can easily observe that it's exponential equation. So we see a function e raised to x plus 1 plus e raised to x giving us a curve like this, and we just want to um, I'll say we just want to reverse it, like the parts over here should go up here, and the parts over here should go down here. So I'll take a check on the function 1 upon 1 plus e raised to minus x, and that will give me my logistic function. So this will be a function e raised to x, or you might say z. So e raised to z upon 1 plus e raised to z, and I can easily write this as 1 upon 1 plus e raised to minus z. Simple, right? Now all we need to do is apply our gradient descent algorithm. So we'll take a quick refresher on what gradient descent is and the gradient descent formula. So I'll give you a minute to think what's the gradient descent formula. If you know it, well and good. If you don't, try remembering it. Okay, so gradient descent formula is optimizing our thetas to minimize our loss function E. And how do we do that? It's like a trial and error basis. So theta j or theta updated e equal to theta old minus alpha times, that's the learning rate, the, the derivative of our error function by the derivative of theta j or our thetas. Okay, so we'll just see again a quick refresher kind of thing, how gradient descent optimizes an algorithm. So we'll see this again, and it it needs to reach the local max. It needs to reach the local minima. So it will start taking jumps, and then with the rate of change in the error function, it will it will slowly reach to the global minima over here. Yes, that was gradient descent all about. So another question for you all: can we use the mean squared error or MSE, which we used to use in linear regression? So MSE is just the Euclidean distance between the regression line and your predicted line. So can we use this? I'll give you like half a minute to think about it. No, we cannot use MSE in this. And why we cannot use MSE? Because your here again, it's not a regression algorithm, it's a classification type of algorithm. It should give me values between 1 or 0, 1 or 0. uh, it should give me probabilities, and I could score the labels between 1 or 0. Or if I want to do multinomial logistic regression, I can make some boundaries for it. So I cannot use MSE. So now I need to define a new error function. So we'll see what our error function should be. So first things, it should be differentiable. Of course, we are applying the gradient descent, so it should be a differentiable function. It should of course be a function of theta, or else our finding the errors and doing the gradient descent is just a waste of thing. So we need to find a function which satisfies both of these, I will say, rules. And here's a tip: to reach the convergence as fast as possible, and to think of it as reaching the convergence at all, you need to make the function as convex as possible. So I guess most of you understand what a convex function means. So we'll go on and define a new E. So I'll ask everyone, what is entropy? So entropy is the state of randomness. So we have a cool little thing called cross entropy. So cross entropy is basically minus p times log q. In our case, it will be minus y times log y hat, and y are our labels, right? So we can define two cross entropies, of course, CE1, which will be minus y times log y hat, and CE2, which will be 1 minus log 1 minus y hat. So I guess I'm with you till now. If you like face any queries, we'll be more than happy to answer them. You could post them in the chat box, which we have. Okay, so I'm getting two CEs. So in in any case, when you have an algorithm but you don't know what next to do, what do you all do? Apply it on a sample data set or a test data? I'll do that same thing. I'm sure everyone is familiar with logic gates. So we'll take the OR logic gate as a sample dataset kind of thing, and we'll make a table which says y hats, what our expected error should be, CE1 and CE2. So we already defined the CE1s and CE2s over here. So we'll just like make a table out of it. So in the first entry, I see my expected error is 0 and CE1 is 0, CE2 is 0. So just from seeing this much, the first entry, I think CE1 can be the expected error, CE2 can too be the expected error. Now let's see the second entry. It shows me that the expected error should be infinity and my CE1 is 0. CE2 gives me infinity. So this time CE2 got it right. Third entry, my expected error should be infinity. And this time CE1 got it right. And in the fourth entry, we again see that both CE1 and CE2 give us the same value as as the expected error. So can you guys get some pattern out of this? I'll give you some time to think about a pattern which you can make out of this. And that should pretty much be our error function. Because if we like establish a pattern between a function and we get it right in the expected error, it should pretty much be our error function, right? Okay, so you can observe that CE1 plus CE2 gives us the expected error. Let's see this again. So here, if I do 0 plus 0, it gives me the expected error. Okay, right? Here I do 0 plus infinity, it gives me infinity, which is again the expected error. Here, when I do infinity plus 0, it gives me infinity, which is the expected error, and so on. So we easily see that CE1 plus CE2 is actually giving us the same value as error. So this can be our error function, and we'll call this for time being as a binary cross entropy. So what next? Okay, so we'll put this binary cross entropy, which we think is the error function, as E in our original gradient descent formula. So let's substitute. So you might be thinking that dou BCE by dou theta j, and so this is our dou BCE by dou theta j, and I'll simplify it into something like this. Now, how I did this? So this is just basic chain rule, basic calculus. So you can see dou BCE. So first you take these two terms, the first term over here, the third term over here, and if you apply like a chain rule on this, the first term and the third term when multiplied give us dou BCE by dou Z or dou Z. Now let's take the multiplication of this first term and third term and multiply it with the second term. So what this gives us is dou BCE by dou Z into dou Z by dou theta j, right? So that is that is equal to dou BCE by dou theta j. So it was just some basic chain rule. And now we'll put our values which we have for dou BCE by dou y hat, dou z by dou theta j, and dou y hat by dou z. We already discussed our function 1 upon 1 plus e raised to minus z. We already have the binary cross entropy. Now all we need to do is substitute in this equation. So we get this expression. Now we'll write it. So our data is pretty much in a matrix format. So our data is pretty much in a matrix format, and this is for this is for just a single value. So we'll scale this up and write this in a matrix format. So in a matrix format, this will be, we'll call the number of entries to be m for a single feature, and we'll write this as summation m minus 2 times y minus y hat. So the mathematics behind this is a bit complex. So if you are interested in this and how I got from this part to this part, I have a research paper about this, and I'll be sharing with you the link of it at the end, and you could view that if you are interested in knowing what actually happens from this step to this step. So this was a dou BCE by dou theta j, and we'll put it in the original gradient descent equation. So we get theta updated equal to theta old minus alpha by m y hat time minus y. So this is transpose, and this is our X matrix. So um, so now we are done with the gradient descent formula, and all we need to do is apply it on our data sets. So yeah, as I told you, if you face difficulties from this step to this step, you could refer to my research paper on this. So now we'll do live coding on real life data sets, and we'll use some data sets from UCI machine learning repository. So if you don't know what UCI machine learning repository is, it's a website maintained by University of California where there are various data sets for you to practice on. Okay, so now we'll actually convert the math which I told you into code, and we'll be using Python for this. So most of you might know about Python. So I've decided that it would be best if we could uh, use Python in this. So we'll code from scratch the algorithm and convert the math which I was talking about into code. Okay, so I want you all guys to follow along with me. That would be best, I think, if you could follow along, and this should truly be a live coding session. So whatever I do on the screen over here, you can do the same things from going on to this link bit.ly alg underscore from underscore scratch, or you could scan the QR code over here. So I highly recommend you all to follow along with me. So this would also give you a clear understanding of it. So you guys can go to this link and get started. If you face any queries, you could post them in the chat box. Okay, so just a second. Okay. Okay, I think there's some technical error. I'll just try doing it once again. Just a second, guys. I think there's some technical error with the app. Okay, so here we are, and I think you all must have opened. Um, so you all must have also opened the link, so we can follow along. If you have not, I'll flash the link once again for you all. So it's bit.ly al underscore from underscore scratch. Okay, so let's get started. So this is just a description of the data set, and so this is also a website where you can follow along. You'll not need to download this notebook and use Jupyter notebooks on your local environment. So first, yeah, we'll import the libraries, and yeah, we'll first process the data and take in our data set. So yeah, and we we'll use the breast cancer dataset which is available on the UCI machine learning repository, and you can also view some of its information or like the dataset description in the part in like the in the markdown about this cell. Okay, so we'll first do some pre-processing for the data, and we'll print out the data set in a as a data frame in a pandas data frame. So we see that there are 9 features, and we have label which was earlier 2 and 4, and now we have converted into zeros and ones to implement our AI algorithm, and we'll be using the same logistic regression algorithm which we talked about earlier. Okay. So next we'll make a feature wise scatter plot, which is feature x1 versus label, feature x2 versus label, and we'll fit a linear regression line on this. So for this, we'll be using Seaborn to make this visualization and see why we want to use logistic regression in this data set. So we are plotting x1 versus label over here, and you can see how bad a linear regression line fits on this. And seeing the data set, it is obvious that we would want to use a logistic regression curve on this. So we'll make a pair plot, which is again the x1 versus label, but in a histogram format. So we know where most of the density is, and you can see that we are getting a particularly high density in the x1. So x1 might be a feature which contributes the most to the to the type of cancer which this dataset shows, benign or malignant. So we'll then make a kernel density estimation plot, which also gives us some statistical information about it. So next, we have 9 labels, 9 features. Sorry, my bad. So 9 features aren't too many to work on. So there might be no need to do principal component analysis, but this technique is specifically useful when you are working with genes and AI, like genetic AI, where you have 500,000 or maybe even more features. So uh, PCA is just extracting the principal components. So we'll pretty much change the axis and then get and like try to convert the 9-dimensional data which we have. If you're also including the labels, we have a 10-dimensional data. So we try to reduce the dimensions of the data. So in this data set, PCA doesn't give us uh, pretty good results, but you could actually see this and also uh, see the code for this, see what happens inside PCA. So I've left this part for you. We'll go on. Yeah. Okay. So yeah. So here we are. We'll now convert our data into a NumPy matrix. So I guess you all know what matrix is. And NumPy is a library which allows us to do calculations easily and fast. So we'll convert the data into a NumPy matrix. So you'll actually see what these epochs and alpha means a bit after. And we'll also make a x0 or our theta's matrix, and we'll fill it with zeros as a thetas. As in starting, you can take a assumed value of theta as we discussed. So I'll take the value to be 0 for starting. However, there are also many algorithms on how you should like choose a theta at the start. So I guess all of you know about what's a train test split. So that's what we are doing over here. We are making a training and a testing split in a 20/80 ratio. So now we come to the main part, which is defining our binary cross entropy or our error function and the sigmoid function. So this was the sigmoid function we discussed about 1 plus 1 up 1 upon 1 plus e raised to minus z. So I made a function for it, and this was our BCE. For BCE, we need x, y, and theta. So we'll make a prediction which will be sigmoid function x of x and x transpose. So if you remember, we were multiplying x and x transpose, and it's a dot product. So numpy has you covered with a function called np dot dot. And then we'll apply the same algorithm CE1 plus CE2. So this much part is CE1, this much part is CE2, and we'll add them both and return the mean of it, which will be our binary cross entropy. So now we come to the part when we actually apply our gradient descent algorithm. So first I'll define a gradient descent function. So for gradient descent, if you remember, I need x, y, theta, and alpha. We have already found out the equation. So now I'll convert it into code. So first I'll get my loss, which will be x into t transpose. Okay, sorry, theta transpose. I'm sorry for this. I got confused with some variable names. Okay, so my loss will be h minus y, and y is our current value which we are thinking about, and then I get the theta from it for the current iteration, and then all I do is return theta. So I'll check binary cross entropy for a single epoch. So if you know what an epoch is like a single try. You could take it as analogy with a single try. So here I have calculated theta or the um, I have calculated the theta with a gradient descent algorithm for a single epoch and printed the cost functions. So you can see that my cost function over here has decreased a bit. It's a small decrease, but we see that our gradient descent function is actually working well. It decreased the cost for us. And we can also print out the theta which was found out for the single iteration, and we see it's a matrix with all of them. So now we'll actually start with the logistic regression. We'll actually start with the logistic regression algorithm. And so I've defined a logistic regression algorithm where all I'm going to do is update the thetas, calculate the new loss, and see if I'm going in the right direction. So I'm calculating the loss with the function which we used earlier, BCE, X, Y, and theta. And remember that alpha over there, that which was a learning rate. So my my change in loss needs to be greater than my learning rate, or else if it's greater than my learning rate, I'm good. If it's less than my learning rate, I say I have optimized the model as good as I could. So let's go down and we see that gradient descent has done a pretty good function of reducing our cost function and our losses. And finally, we print out the loss which we have got on the training data set and use the same thetas to test the loss which we received on the test data set. So our loss for the test data set is approximately 0.15, and which is a good score for our algorithm. So that was about. So now we just converted the math which I spoke into code. You see, it's so easy. Now we'll actually see what as okay, yeah. So now we'll actually see what Azure AI has for us and how it can make things even easier for us. So Azure AI services, there's a vast amount of services. You have cognitive services which can work on cloud and edge. So we go from pre-built AI to custom AI, and we also have conversational AI in Azure services. So we'll also see a demo on this and how you can use it yourself. And the best part I think is you can use any deep learning frameworks or any third-party frameworks like Cognitive Toolkit, TensorFlow, Caffe, Theano, CNTK, any which you like actually, and deploy your algorithm on Azure and deploy the model on Azure. And Azure will take care of the infrastructure with compute. It has AKS, Azure Container Services, IoT Edge, Spark datasets, Cosmos datasets, PostgreSQL, and so many more. It also offers you CPU support, FPGA support, GPUs too, and we'll actually see how we'll configure a GPU in some time. So you also have some Azure ML libraries, and you can code directly from VS Code. You also have Azure ML Studio, in which you can write your model without having to write a single line of code or minimal code. So Azure AI has us covered. So I'll just show you a short uh, video kind of thing, or a demo, like illustration, to show what Azure AI has. Okay. Okay, so again there might be some technical error, so don't worry. I'll tell you about what Azure AI has for you. So for Azure AI, you can easily develop the model in any of the third-party applications, as I told you, and then you can use ACS, or the Azure Container Instance, to deploy your algorithm into auto scaling node pools, and you could even manage that with Kubernetes. Azure is equipped with Kubernetes too, to efficiently manage your containers, and many of the large Docker image companies. Like you could use Docker Hub and so to upload your image. So we also have conversational AI. Uh, so we have also already discussed about the custom AI part. So we'll take a look on the conversational AI. This was already covered in the previous session, but then there's this uh, like a flow chart to like understand what Azure can do for you. So now we'll get started with the CNTK code and visualize the data sets. So CNTK is a behind the scenes magic that makes it possible to train DNNs, deep neural networks, that address a diverse set of needs. CNTK lets anyone develop and train their deep learning model at massive scales. So you can scale up, and successful deep learning projects also require few critical infrastructure requirements. So we'll also talk that in a later part. First, let's get started with the code. And similar to last session, we'll have this hands-on, and I'll highly recommend you to follow along with me. Okay. So yeah, you can just a second. You could use this link or QR code to get to like be on the same page and get the code which I'm using. So the link is bit.ly CNTK demo. Note the link is case specific. Okay, so let's get started. Yeah. So we'll see like an analogy of what we would want to do in CNTK for building the same logistic regression algorithm. And we'll also explore a different data set this time. We'll use the MNIST data set. So MNIST is like handwritten numbers, and we like classify the handwritten numbers. I also have some links over here if you want to code this in brain script, or get more info about the MNIST dataset, or download it. So I'll skip this part where we just install CNTK to get ready for the live coding. So what's the problem over here? I already mentioned this. The problem is OC, optical character recognition. We need to like classify handwritten numbers. So first we'll show a sample image from the data set. So these are the kind of handwritten numbers which I'm talking about. And our goal here will be to train a classifier which can correctly identify the digits in the image dataset. So the 5 stages of AI are also applicable here. First, we'll read the data, we'll process the data, we'll create a model, and we'll learn the model parameters, and finally we'll evaluate the model and score it. So let's get started with data reading. So CNTK has a very cool feature, which is CNTK text reader, which makes data pre-processing extremely easy. So yeah, so this is like optional section, which uses magic functions. You could read this. So this is just so we are just importing some libraries. Yeah. So first for the CNTK text reader to work, first we need to show how many classes we have. So 0, 1, 2 till 9, we have 10 classes which we want to classify the data in, and input dimensions which you could get from the data set itself. So here is a bit of data reading part and what the image data set, the format of the image data set. So, so this is just a section to download the data, and you can directly run it. We have some links from where we'll install the test and training data sets, and we'll also want to save the data in a CNTK text reader compatible format. So we'll convert the data into a CNTK text reader for compatible format, and then we'll finally use the CNTK reader to read the data. It's not something that great, so you could just check it out yourself. And we'll finally get on the part where we'll create a logistic regression algorithm. So like we earlier solved it with a logistic regression algorithm, this time we'll use DNNs. So let's get started. So I've just taken the input and the labels. So you see CNTK actually makes it very easy for me to get the input variables, to get the labels, to get the features. I could get them in just a single line of code. Whereas if you remember the last one, the last Python algorithm which we saw, we needed to specify list comprehensions and things like that. So we'll not have to do that now. So yeah, so as such, scaling is not actually required in logistic regression, but we use scaling to reach our convergence point faster. So I guess you all know this. We need to scale the input from 0 to 1 range. So we'll scale each pixel in the data uh, to 0 to 1. All we need to do is divide it by 255. So next we'll use the softmax function. So softmax function is activation function. So now we'll again define our loss. So remember in the earlier part when we were doing this with Python, we had to define a full function where we define the binary cross entropy, wrote the formulas for it, use some numpy functions. But CNTK and Azure AI has got you covered. You could do it with just a single line. You could write C dot cross entropy with softmax, Z comma label. It's that easy. And a model is created. So now let's take a look again at the model which we created. I had not covered this part earlier. So as I thought it would be best to first take the uh, take the output of show the output of the network and tell about the logistic functions. So creating models with CNTK and Azure AI is as easy too. All you need to do is make a function, create model features. You have got a c.layers.default options where you can specify the number of layers, you can put in dense layers and things like that. So it's as easy as this, and with just few lines you're done with some good code. So yeah, I've defined the loss, and I have also created the model in Z, which will represent the output of the network. So now finally, any algorithm is like insufficient without evaluating the model. So we'll evaluate the model and score our model. So earlier we had to do thing like define the BCE and take the final BCE which we obtained and print it out as the final error. But CNTK, all you need to do is CNTK or C dot classification error as you have defined it, and pass in the output of the network and the labels, and you are done. So we'll so now we'll finally use the stochastic gradient descent to minimize our loss function. So similar, we are defining the learning rate and the learner. So here you can see that we are using the SGD or stochastic gradient descent. So first we'll create some helper functions, which will be just like print the training progress or print the moving average for us. And finally, we run our trainer. Okay, just a second. Okay. Okay, so I'll just continue. So we can then define the mini batch size or the batch size in which we want our stochastic gradient descent algorithm to work, and then just run the trainer. So you could try this yourself too. So now we come on the part how I can deploy this on Azure. So what we want over here is we want our teams to perform rapid experimentation, scale based on the demand of training, and handle the increasing load which is needed to serve a trained model. So as I told earlier, we'll see like how we can use GPUs with Kubernetes and allow the clusters to facilitate running frequent experimentations, and also use auto scaling. So the process involved is we'll deploy the Kubernetes cluster using the ACS, or also called the ACK, Azure Container Service Engine. Test our NVIDIA drivers, NVIDIA GPUs are loaded correctly, and finally run our CNTK Docker image. So, so this is basically the architecture you would want to follow while using the ACS. So we'll see this in a greater detail. So you would want to make a single container which acts like the master container, and make some GPU enabled slave containers. Okay, so with that container and node pool, you'll be done with the infrastructure part. Now, all you need to do is check for the NVIDIA drivers and then finally run the Docker CNTK image. So you have a wonderful function by Azure called Azure GPU minus test, and you can run the Azure GPU minus test job. So using the first command, which is over here, create minus f Azure GPU minus test.yaml in a YAML file, which we, or configuration file, which we like discussed. So this will create the jobs for us. This one, if you do kubectl get jobs, so we are using Kubernetes to do container orchestration. So you should see a GPU job being made, and with kubectl get pods, you should be able to verify the name of pods where it is running. Usually the naming convention is something like the job name and a character identifier. Once the job is completed, you can get the logs and check at what happened. So uh, you can just do kubectl logs. So note that this minus 83 ngh is a unique identifier which might be different in your case too. So we also want to implement auto scaling. So auto scaling is a pay for what you use kind of service, and Kubernetes provides you both pod level scaling and node level scaling. So HPA or HPA lets you specify node metrics that are tracked, and when determining whether new pods should be added or removed. In addition, with this, you can also add node level scaling, and both of these could work together. So you could add new Azure virtual machines when the number of resources available in a cluster is not sufficient to meet the expected requirements. And Azure allows you to do all of this simply. So we'll actually check what we need for the auto scaling part. So this is a Kubernetes job, which I've highlighted over here, which specifies the GPU requirements, which I need. So so coming to the auto scaling part, so we'll see this flow chart. So when a new job first gets submitted to Kubernetes, or you have a new request, it is first placed in a pending state. Then a kube scheduler comes in and determines if there is any work to be rescheduled. In such a case, there is a pending item which we call X, and we have three nodes, but there are no nodes with free capacity. So it returns, okay, I have no nodes with free capacity. So then Kubernetes ACS autoscaler comes into picture, which runs like a control loop and notices, oh, okay, so it sends, do we have pending pods? So so we receive that, okay, I have a pending pod X. As there are no more available nodes that can handle the request, it provisions a new virtual machine. So I am creating a new VM, and in the Azure deployment, when this is happening, you can view the deployments running in the Azure resource group, and you can see an active deployment being made. So now this process repeats again for node level auto scaling. So the kube scheduler again asks if there are any stuffs to schedule, and now we'll find the newly provisioned node D with free space created by the Kubernetes ACS autoscaler and Azure Container Services, and PodX is placed on node D. Done. So that's all we needed for node level autoscaling. It's so you can see it's easy to implement this on Azure. So now we'll also see um, like cloud-based web service for our model. You can easily create this kind of web service for your model, where you could test request response, batch commands, and you could also consume the model make a Swagger API for consuming the model, and things like that. Azure allows you to do this just with single clicks. So using Azure is as easy as this. And if you want to know about the codes which we can use for consuming the model in languages like C Sharp, Python, R, you could go on to my GitHub and I have the codes for it uploaded over there. I'll share with you my GitHub link, GitHub repo link. And yeah, you could also clone this and replicate this, experiment a bit on this project, uh, and it is hosted on Azure AI Gallery too. So finally, we see a web service for image classification, and I will recommend you to always make a web service which can easily run in JS or P5, use something like P5.js, and you would want to make your web service or your model available as a web service in a P5 or in a JS format. So you should be able to test your model. You should be able to test your model with a web service in JavaScript. So I have used something like something called a library called p5.js. Most of you might be knowing about the library too. And you could just use some simple commands which you can also find on the Azure documentations, and you could make a full-fledged web service with p5.js, which is fast enough and easily deploy your model for a request response web service. And you could also live test this, and all this is a simple JavaScript code. So as we are running low on time, I'll not show you a demonstration of this. However, you could go on to the link shown over here and try the demo yourself. So it's like a basic image classifier which I've built, and so this might seem a bit funny, but it's an image classifier between a mobile phone and a human face, a two-class basic image classifier for demo purpose. So the other thing which I wanted to mention in this is Azure allows you some wonderful features, like this is just an example with 1,000 images. So I've made the data set myself. So I have not taken 1,000 images myself. Okay. So I just took like 100 or 200 images. So how do I get a 1,000 image data set now for a greater prediction? I use something called Bootstrap. So you can understand Bootstrap method as you have got fixed money to invest in assets, and you will increase the number of and you'll increase your money. So in a similar way, Bootstrap is algorithm which treats data like a population, and you could not only create permutations of the data itself, but generate data from the data set itself. And another thing which I wanted to mention was that in a Bootstrap algorithm, all the additional rows of data which are created have the same probability, so there's no bias kind of thing in machine learning which it imparts. So that was about an AI algorithm. Inside an AI algorithm, how you would deploy it on Azure AI platform, and 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 some of the wonderful things which Azure provides you. So for further details, you can view my research paper. It's machine learning as a decision aid for breast cancer diagnosis. But it's not just limited to breast cancer diagnosis. I've mentioned some techniques which I've showed here too, and you could read this for more info. So this is about me, and you could scan this QR code to know more about me. And these are some links if you want to get in touch. Yeah. So that was about Azure AI and how you would want to uh, deploy an AI algorithm and Azure. So if you have any questions, we are good to go. Uh, you could post the questions in the chat box which we have, and I will try our best to answer them. And thank you. Yeah, all of my code is available on GitHub, so you could like see the GitHub link. And yeah, thank you.
So Rishit, you have a question from Prajot. He says, like, what will you advise to the folks who are getting started with ML and AI and ready to give 6 to 8 months or more to master it? How should we approach any specific sources for learning?
Okay, so I think this is a good question and it can help all starters too. So I think most of you might be on Stack Overflow. So I had shown you Stack Overflow link, and I have an complete article on how you should get started with AI, some resources too. But I'll also tell you about the resources now. So first, I would advise you to do the Andrew NG course, which is available on Coursera, for getting started with how actually what happens inside an AI algorithm. Then there's also an course called Statistical Learning by Stanford University. It is a 2016 course, and you could see that too. And for other parts, I think Microsoft and Azure AI has wonderful resources. It has completely got you covered if you want to get started. And if you're an expert, then too it has got you covered. So you could browse through the documentation. It has wonderful README files which you could browse through. They also have a GitHub repo where you could actually see the Azure ML code, and anytime you could take like an open source library like the CNTK which I showed you over here, or try or start with Azure ML. You can always deploy it to Azure. So I think that should answer the question.
Yeah, Rishit, thank you.
Yeah. So this demo is ready. I think we can. You can wait for 2 minutes, and I can show you this demo. You can try this demo at home too. But I'll just show you with this demo. Okay. So just ignore that warning. It's nothing great. So as you start the demo, it takes some time to load as it needs to fetch the algorithm, the callbacks. So it will ask you, do you want it to allow use your integrated webcam? You might want to allow it, and then you can see I'm being recorded, and it's showing me class one over here. So that's a human face. Now I'll just cover my face with my mobile phone, which is over here. So I'll just like cover my face, and it's showing me class 2. So that's a simple web service which gives me live streaming of my results too. So you can try this, view the code for this. I have it open sourced. So do we have any more questions or any queries?